Assalamu alaikum. We are continuing with our discussion of polynomial approximations to some common functions. In the last lecture, we discussed why are we looking for polynomial approximation to some common functions. So today we're going to see some examples of that. Now, let's take an example, very concrete example, e to the x. Want to approximate f of x e to the x with a polynomial. Okay, there are still some questions that need to be determined. Do we want an approximation? Do we want the approximating polynomial to be a decent approximation of e to the x over the whole number line? Well, that is going to be hopeless. Yes, we already know from our previous experience and understanding that any exponential, such as e to the x, will beat any polynomial in the long run. Right? Which means when you go more and more towards infinity, the exponential will be so much bigger than the polynomial. I mean, you cannot call it an approximation at that point. Right? So, we cannot be that careless in stating this. We have to maybe say that we want to approximate f of x equal to e to the x with a polynomial near a value, meaning we fix some value and around that value our polynomial is a decent approximation. So, want p of x such that p of x is approximately f of x for x values near some value c. And we might as well add the condition that the value of the polynomial at that point exactly equals the value of the function, in this case e to the x, at that point. Graphically, let's see what we are talking about here. This is the graph of e to the x. Let's say our c value is 1. Okay. So this is the value of the function. We want some polynomial that over there has to go through that point, because we want p of c equal to f of c. So the polynomial, let's say this is a polynomial. Okay? But there can be many polynomials that go through this point, right? I mean, something like there can be many polynomials one could draw that go through that point. So, to make this problem a little bit more limited and easier to identify some obvious targets, maybe we can also demand that the polynomial has the same tangent slope there as the function itself. Right? In other words, we want somebody like that. So that at c, it has the same slope as the original function. Okay? So let's write all this down and actually calculate one particular example. Okay, so approximate, so here's an example. Approximate f of x equals e to the x with first degree polynomial. First degree polynomial means the highest power of x is 1, right? So let's write this down algebraically. What are we asking? Approximate f of x, okay, right? So I've forgotten something, right? I haven't specified near where. Let's say approximate f of x equal to 0 with the first degree polynomial at, let's take a very simple case, at c equals 0. What do we mean? In other words, i.e. find p of x, let's call it first degree, I will put a subscript 1 here, equals a naught plus a1x, right? This is the general formula of a first degree polynomial, such that f of 0 equals p1 of 0, and we also said let's make the slopes of the two functions equal, the approximating function slope equal to the original function. F prime of 0 equal to the slope of this function at 0, and the we'll say f of x is approximately p1 of x for x near c. Okay? Alright, so we have some conditions here, right? We can use these conditions to solve for the unknown constants here. The term, the 0 degree term and the coefficient of x to the power 1. Let's do that. I'm going to erase this so I have more space. Okay, let's erase this part. Okay. So these are our requirements. So how much is f of 0? This is e to the 0. This equals 1, right? Which should equal p1 of 0, which is how much? If I plug 0 in here, I get a naught, or a sub 0. So a sub 0 should equal 1. Similarly, if I incorporate this other condition, that the derivatives are equal at 0, f prime of 0, right? F prime of e to the x is e to the x again, right? So here's again e to the 0, which equals 1, which equals p1 prime of 0. Now how much is p1 prime of 0? The derivative of this function is a1, okay? So it's a1. So putting these two conditions on our function solves our two constants, a0 and a1 equals 1. It gives us that p1 of x is the function 1 plus x. So here is the first degree approximation to e to the x near c equals 0. Let's look at it graphically how good approximation it is. In other words, we'll plot e to the x and we'll plot this function we found. This is our e to the x, and the point we're working with is at c equals 0. And what is the function we found? It's the linear function with slope of 1, intercept of 1. So it has to agree with there, and it has slope of 1, intercept of 1. This is our y equals 1 plus x. Okay, well, it's an approximation, right? You will notice that for values very much near 0, it's not too bad, it's not too far away from e to the x, on both sides of 0 actually. But of course, if you are out here, then this guy's here, whereas the e to the x is way up there. Okay? Now, how could we improve our approximation? Keeping the same c, near c equals 0, can we do better? Well, one degree of freedom we have is to go for a higher degree polynomial. But the higher degree polynomial, how is it going to help us? How are we going to find the constants? Then maybe perhaps putting more requirements. So far we had the requirement that the value at c equals 0 and the derivative at c equals, the value at c equals between the approximative function and the original function, and the derivative at c equals of the two functions, the original and the approximate. Now we can require that the second derivative also equals. Okay? So let's do that. Let's go for example number 2 here, where we're going to find second degree approximation to e to the x. And I should mention that as we're doing this, this is a very common theme in mathematics, that once we discern some procedure that helps us to do approximates or get at something, then the next obvious question is how we can refine that procedure to go either more accurate, better approximation, so on and so forth. Okay, so what do we want? This is example number 2. Find second degree polynomial approximation of f of x equals e to the x, and we'll keep the same c value here. We're going to work with c equals 0 here.